The impact of human activities is putting our carbon sinks, including forests, grasslands, rangelands, and agricultural farmlands, under threat of extinction. To counteract the destruction of these life-supporting ecosystems, the sustainable HCI community has advocated for the design of tools and interfaces that support conservation efforts. However, to ensure the practical success of these efforts, there is a need to understand how real-world users of these tools might perceive and utilize them, and how their goals, values, and constraints might affect the design of technological solutions for the environmental crisis. In this work, we present the results from a qualitative user study comprising 14 semi-structured interviews with subject matter experts from different domains of ecological restoration, including agriculture, wildfire management, post-fire reforestation, and rangeland management. We used a novel bio-inspired tool called the eSeed as a research probe in our study to present the interviewees with a tangible example of an autonomous reforestation tool and elicit creative ideas from them on how or where technology can be used. There are two main contributions of our study. First, we report a core set of existing challenges, application opportunities, and economic and regulatory hurdles for technology in natural and semi-natural ecosystems. Second, we present design considerations for HCI researchers for building and deploying novel devices and interfaces in nature, and discuss implications for future research in ecological restoration. We believe that this work will help HCI researchers identify user needs and discern opportunities for environment-centric work within HCI, and help them understand the constraints affecting the design of conservation technology. By following the design guidelines presented in this work, HCI practitioners can solve for a diverse set of environmental problems and ensure success in terms of scalability and adoption. Our participants included 14 subject matter experts from North America working on different facets of ecological restoration. After defining our key research questions and recruiting our participants, we conducted semi-structured interviews with them. We generated and anonymized our transcripts and followed a thematic analysis approach in which we qualitatively coded the data and created code groups that were later grouped into themes. Of our 7 code groups, 3, namely challenges with current practices, application areas, and feasibility, were directly transformed into themes, whereas the other 4 were grouped into the larger theme of technology features and design considerations. We saw that when it came to challenges with current practices, dominance of invasive species, expensive and hazardous post-fire restoration, ineffective wildfire management systems, and unsustainable agricultural practices were key issues facing land managers and growers. Our interviews revealed that technology has a key role to play in solving for current challenges in ecological management. Specifically, technology that promotes growth and re-establishment of native species and endangered pollinators and allows for targeted delivery of herbicides was deemed crucial to tackle the invasive species problem. Tools that could accelerate post-fire revegetation and allow for landscape monitoring were thought of as important to restore burnt habitats. For wildfire risk management, early detection systems with a high temporal and spatial accuracy and tools that could inform prescribed burns were of value. Finally, novel planting tools and technology that allowed for subsoil delivery of materials were highly merited in agricultural management. We also saw that for technology to be adopted, scaled, and taken seriously by land managers, it needs to be aligned with current legislation and regulatory policies. Presenting trial data with superior performance and cost benefits, conforming to stakeholder objectives, and taking values at risk into account were other important factors to ensure the real-world applicability and feasibility of the technology. Our last theme, technology features and design considerations, highlighted important design guidelines for HCI practitioners looking to create tools and interfaces for ecological restoration. We learned that by coupling different sensory and imaging toolkits together, such as a combination of aerial imagery with ground truthing or by using novel visual indicators to create high-tech monitoring systems, technology designers can increase the dimensionality of environmental data. Additionally, by designing direct actuation mechanisms that support the delivery of payloads in the soil or that respond to environmental stimuli to trigger a response, designers can create a more holistic ecological toolkit that is currently dominated by sensory devices. To enable resilience in large-scale unmanned deployment scenarios, practitioners need to design for mechanical integrity and energy efficiency and build fallback mechanisms to account for unpredictable environmental effects. We also saw that to account for differences in soil types, geography, terrain, climate, and other local conditions, designers need to build flexibility into their devices to be able to adapt to different environments and users. While the design of novel systems was encouraged by our experts, we learned that sometimes leveraging and augmenting existing tools and technology can enable faster and easier adoption of technology in environmental settings, especially by conservative users. When designing technology for environmental applications, many of our experts suggested taking guidance from evolutionary principles in nature and mimicking features present in naturally occurring species and processes to create resource-efficient, adaptable, fault-tolerant, and scalable devices. Finally, we saw that biodegradability and compatibility with nature were seen as crucial elements for tools that needed to be deployed for long periods of time in natural ecosystems. Bioresorbable materials, electronic-free designs, and mechanisms that could enable retrieval of non-biodegradable elements from the landscape after the duration of use were seen as highly valuable. Aside from the challenges, technology applications, feasibility concerns, and design guidelines reported in our work, our interviews also emphasize the importance of engaging diverse stakeholders in all stages of the design process for future sustainable HCI research. Additionally, HCI researchers working on conservation technology need to take into account both the ecological history as well as the changing ecological profile of the landscape in question. As such, technology design should aim to promote resilient ecosystems and ensure the persistence of key environmental entities and assist post-disturbance recovery in damaged ecosystems. Ultimately, our research hopes to inspire future efforts in the service of producing more viable human-nature interaction.